Yeah, or on the sofa.
You want me to sit on the sofa and
Yeah,
present?
yeah. No, I'll introduce you guys.
Really?
Yeah.
No, you can present.
No. I mean, let me first go around.
During the presentation, I stand up.
Yeah. Yeah. Okay, good afternoon. So let's begin the first session in the afternoon. As you can see from the title, Keeping It Fresh. So that's an exciting title. So we have been talking a lot about agriculture, sustainable intensification, food production. So one of the things we need to keep in mind is how to do in a way so that we manage the resources sustainably. So more food is needed, but at the same time we need to manage our water resources, surface water, groundwater, ecosystem services. So this is what the focus of the session. And as you can imagine that we are the #1 food exporting country, and there will be a lot more pressure down the road to export more and more. So how do we, in order to meet that demand, we have to produce more with tightening or limiting resources, and at the same time do well so that our population which produces the food doesn't suffer from the impairment of the surface and groundwater. So with that, we have assembled a panel with 4 distinguished members, ranging from I think this is also a part of our local to global connection. So from locally, we have 2 states representing, Nebraska, Iowa, focusing on groundwater and surface water respectively. So, and then regionally, the Missouri Plains, and internationally, Rwanda, Africa. So with that, I first, Nebraska will be represented by Brian Krienke from the University of Nebraska, Iowa, Matt Helmers, and then from the Great Plains region, representing Martha Kauffman, and the Africa and global, Richard Ferguson. So the first speaker is Brian Krienke. He's an assistant extension educator with the University of Nebraska. He received his PhD here at the University of Nebraska. And then the second, Matt Helmers. He's Dean's Professor and the Director of Iowa Nutrient Research Center at the Iowa State University at Ames, Iowa. Martha Kauffman is the Managing Director of the Northern Great Plains region of World Wildlife Fund here in the US. And then Richard Ferguson, he's the Vice Chancellor for Rwanda Institute for Conservation Agriculture. It's a new institute, but he has also roots here. So we just have him take that position about 6 months back. And with that, we'll begin the session. Brian?
Thank you, Dr. Ray. I'll just use that. Thank you, Dr. Ray. And thank you, everybody, for coming to attend. So I'm going to talk about nitrate contamination in the groundwater in Nebraska. There we go. But first, I'd like to acknowledge a thank you, before we get started, so I don't forget at the end. First of all, thank you for the invitation to be able to speak to you today, University of Nebraska. And then the names you see here are a subset of all the people that have been involved in the projects that I'm going to talk about today. The growers, it really takes a large team effort that I'm here in front of those people presenting on behalf of, but without their help, it wouldn't have happened. So to set it up, just a very brief introduction, at least for people in Nebraska, we have, it's pretty common knowledge that we have a widespread nitrate contamination issue in our groundwater. The legal drinking limit is 10 parts per million of nitrogen. And if you look at this map of the state, you'll see levels that are red or dark red are above that level of 10 parts per million. And in some instances, they far exceed this. So how did this happen? How did we get here? It's predominantly associated with irrigated corn production. And we have roughly 70% of our irrigated row crop acres are corn, and they're predominantly located in the central and eastern part of the state, which we show here on this chart. So some of the overriding factors that come to bear that make this the issue that it is, and I'll show you on the next chart kind of the progression in time of how this contamination came to be, is the predominance of irrigated agriculture, as I said, and that's on the left chart, and you can see just how well it's correlated with those yellow outlines, and those yellow outlines represent areas where the average value is 10 parts per million or higher. And on the chart B, or on the right, you can see that this is combined with soils that are really well drained or excessively well drained. So we're growing a crop like corn that takes fertilizer and nitrogen nutritionally to grow. We have to supplement that every season. We have to add water to that, and in order to also grow the corn, those two together, nitrate is very soluble in water, leaches, and it leaches more easily, of course, according to the soil type, and so this demonstrates that. So a little bit of a breakdown on our irrigation acres, east versus west, so to speak. If we look at the east, it's associated with more precipitation, but we still have gravity irrigation, and then predominantly center pivot irrigation. And there's less of a discrepancy in areas that are associated as high nitrate, which are the orange parts of the charts, versus low nitrate, which are the blue part of the charts. But if you look at the west, it's more arid, takes more irrigation to supplement the corn that's produced there. There's a predominant, there's more association with the gravity irrigation. So it's going to require more irrigation by the grower, and if you irrigate something more inefficiently, such as gravity irrigation, it's likely going to be more associated with leaching and nitrate. Here's the timeline then. So, basically, when did it actually start? It started the day we started applying fertilizer and nitrogen. And I'm not trying to be a bearer of bad news. I'm certainly not against corn production or anything like that. But that is the association. It's very clear in the literature. And as far back as 1974, we can start to see it develop, and that's in the upper right part of the chart there. You start to see it really predominantly associated with the most vulnerable parts of our state. And when I say vulnerable, I'm talking they're well-drained soils, they're fairly shallow, unsaturated zones before they reach the groundwater, and the predominance of irrigated crop or irrigated corn production. And as we progress through time, we start to see the map that's in front of you enlarged, which is this predominance up in the northeast part of the state. Those are quite varying in depth of the unsaturated zone, but safe to say it's more associated with much deeper sands, excuse me. And so it just took longer for the same process that occurred in the central part of the state to start to show itself in the northeast. Now, one of the things that we can combine a chart from 1974 till now is because, unfortunately, the problem is not really getting that much better, with the exception of maybe one bright spot I wanted to point at, and that's next here. So Richard Ferguson, one of our panel members, this is from a paper he did in 2014 in the Central Platte portion of the state, and that's kind of where most of the research has been taking place from when I was digging in the literature and when I've worked in this. Again, that shallower depth to groundwater, there's going to be a faster return on your investment. So if you implement a best management practice that is going to lead to less leaching, you should start to see the fruits of that labor sooner rather than later. And this chart shows that when they started implementing their groundwater management strategy in 1987, they could only start regulating in 1984. So Central Platte, they created the first groundwater management plan in 1987. You can see the trajectory in the blue circles continuously declining until today. And that sounds great, except on the next slide, you see that it's starting to stagnate, and it's starting to stagnate for several reasons. One of which, we're just not getting any more efficiency gains from the corn that we are producing. So a lot of those gains have been associated with reducing the amount of nitrogen applied, accounting for different sources of nitrogen, whether it be from the irrigation water itself or residual soil nitrate, and better techniques to help the grower with that nitrogen management, but we've plateaued. And the application rates reflect this. And so I think part of the reason this has happened is that we can't shift the paradigm according to the old way of doing nitrogen management, which has for the longest time been based on this expected yield approach. You know, when you talk about nitrogen fertility, it's a guessing game. You have to supplement so much nitrogen to supply your crop, yet you can't store it well in your soil before it's leached. And so from a grower's perspective, they have to make choices. They have to buy product ahead of the time. They have to find logistically when they can get it applied. And it goes back to this concept of how much am I going to need? Well, let's start with how much yield I expect to produce. It takes so much nitrogen per pound of grain. Therefore, it's going to take this much nitrogen. But as you can see in this chart, or maybe that's an unsafe assumption, the blue circles are the expected yield and the red diamonds are the actual yield. And what this shows abundantly clear to my mind is that we're always chasing a carrot, but we're never reaching it. So we're always over-applying with the best of intentions, but it's not leading to the additional gains in efficiency. In a word, it's not matching supply with demand. The crop demands so much nitrogen. If we supply it all up front when the soil can't handle it, it leaches. And this is a chart from one of our extension circulars, which I really like because it highlights the point clear, which is we have a large portion of our growers that are applying nitrogen either in the fall or in the spring, and we're not side dressing, we're not split applying the nitrogen, in other words, and so we're putting it out there when it's most vulnerable. When we have the annual rainfall pattern associated with driving the residual nitrogen values plus what we've added to the soil down through, and that's when the leaching potential is higher. So how do we get out of this? How do we get a better guess at what the crop actually needs? How do we synchronize nitrogen supply with nitrogen demand by the crop? Well, for years now, we've been researching the use of sensor technology, this time for nitrogen instead of for soil moisture. And so there's an array of different sensors out there, active sensors, passive sensors, but they really are doing one thing, and that is they're trying to detect an indication by the plant that it is stressed, its chlorophyll content or its nitrogen content is decreasing. That gives us an early warning sign to say, how can we then respond to that stress and apply, complement it, so we can better synchronize the demand from the plant with the supply that we're giving it. Hopefully that makes sense. So I wanted to highlight two projects that I think do an excellent job at this. The first, as it's been completed, is Project Sense. You may even have heard of that before. It's a joint effort between 5 different natural resource districts in the state. The Corn Board, the USDA also threw in. So it was a fairly large project. And really what it came down to is we need to meet the grower where they are. And so we went to 52 sites with a high clearance applicator with these sensors attached, and we put our method versus their method. And we just wanted to see who's more efficient, who's more profitable. Because in a grower's mind, they have to make a choice. It's easy to gain in efficiency simply by not applying nitrogen, but it's not easy to then match that with an economic return for the grower. So we're trying to achieve both. And what you see here in the chart is a quadrant chart that breaks it down into like a win-win, win-loss kind of quadrant. If you're in the upper right portion of the chart, that means the Project Sense, the sensor-based method, increased efficiency of the fertilizer used, and it also increased profit for the grower if they would have used the Project Sense method when compared to their own. And the breakdown across 52 site years, across 3 growing seasons, is that 62% of the time it was a win-win. Project Sense would have benefited these growers. In some cases quite significantly. 83% of the time we would have increased efficiency. That's a pretty good track record, I think, to go forward on. Then another project I'd like to highlight, this time I was the director on the project, and it was a fertigation research project using the crop canopy sensors again, but a little different logical approach. Project Sense was a high clearance applicator meant to complement that one-time in-season application. So taking a grower that might do all of their nitrogen management at one portion of the season and splitting it up at least twice and having a significant impact as a result. With fertigation, we're saying we have a simple robot out there in the form of a center pivot irrigation system, and we have the ability to distribute the nitrogen with the uptake mechanism, the water. We can do this multiple times. So we took that concept and also compared it against our current best management practices that we recommend as a university. And don't try to read all of these because I'll break it down here. But basically we compared it against the long standard, if you will, cautious with that term, which is an algorithmic approach that predicts how much nitrogen we need before the season begins. And you simply implement that nitrogen rate, as we call it, periodically throughout the season. We compared it versus the Project Sense method, which is labeled as HS, and then we had a suite of different fertigation treatments, which essentially break down into looking at the crop once a week. Is the crop reach a threshold of stress as indicated by the sensor? And if it does, we have to respond with a rate of nitrogen to try to synchronize that nitrogen supply with that nitrogen demand. And so basically we broke it into a fixed and arbitrary rate because we had to, let's try, what's a grower tolerated rate, in other words. So we picked a fixed rate. And then we used a computer model to inform us. And then we had another approach that was a predictive model that would use real-time weather information. Instead of waiting for a sensor to tell us there's stress, it would respond ahead of time. And what the results show there is that the fertigation methods, regardless of which one, was more efficient and more profitable, this is the same type of quadrant chart, than our old standby, the UNL predictive algorithm. So I thought that was really encouraging because what they were doing in the Central Platte and these other areas is they're using that other algorithm kind of as the base to recommend for growers, and we have at least a way to continue to increase our efficiency. Since I'm low on time, I'm going to skip through this and go straight to what I think we need to do because I think I wanted to leave you with some conclusions. In my opinion, we might not be able to do this based on some of the literature I've seen with growing corn alone. We might need to start interjecting other parts into our cropping system. So not just cover crops, which are also, I think, a very important piece of this, which is trying to minimize off-season loss, but also integrating large consumers of nitrogen, large consumers of water, since this is a quality issue, not a quantity issue, that can take nitrogen fertilizer off the land for a certain amount of time so that we can purify or cleanse the aquifer a little more quickly. So it depends on what society is going to tolerate there. We need to stop applying all fall applications, in my opinion. It's a mindset issue as much as anything, and we need to get rid of it. Maintaining living cover crops, and this is the big one, I think. These natural resource districts look to the university to help them with what's a validated approach to reducing leaching or improving efficiency or any suite of information along those lines that helps them with their policy decisions. We need to establish long-term standardized studies that look at nitrogen and irrigation management across the state versus a 3-year study or a 5-year study. We need to be constantly embedded in these communities so that we can validate, when there's cost share programs or policies that are being implemented, are the expected return on investments what they should be? Are they validated by the research? So with that, I need to keep moving to the next panelist. Yes. I'm getting the red card of death up here, so. Dr. Ray?
Thank you, Brian.
Thank you.
Move to surface water issues, and I think we'll take all the questions at the end. We are trying to keep 30 minutes of QA time, so they'll have plenty of questions that time.
All right, we're going to move to Iowa. Similar type situations, but a lot of our focus has been on surface water, although there was a recent report that did some review of private drinking water wells in the state of Iowa, and similar to what Brian showed, we're seeing high nitrate in that shallow groundwater. But we'll talk about where there are some differences in Iowa and some of the opportunities and challenges that we face. So there is increasing concern about our nitrate nitrogen levels for drinking water sources, both urban, rural, and private wells. Probably one of the most the issue that people know the most about or hear the most about is Des Moines Water Works and a lawsuit that they filed a few years ago against 10 drainage districts in 3 counties in Iowa for the nitrogen or nitrate that was coming from those drainage systems. That court case was dismissed because it was determined they couldn't sue the public entity, the drainage districts, and the drainage districts are there to discharge water, not for water quality, but there's been a subsequent suit filed recently with concern about the drinking water from the Raccoon River and high nitrate levels. One of the other things that has driven some of the work around nitrogen more recently in the last 6 years is related to the Mississippi River Basin, hypoxia in the Gulf of Mexico. Iowa, while maybe only 10% of the land area contributing to the Mississippi River, contributes upwards of 30% of the nitrogen to the river, in some years much more than that, depending on some of the weather conditions. And the goal relative to hypoxia and the Hypoxia Task Force Action Plan, that lower right box there, the recommendation is that we need to reduce nitrogen and phosphorus loads down the river by 45%. One time the goal was to do that by 2015. We didn't meet that goal. Now it's been 2035. At the current rate that we're on, I think it's unlikely we'll reach that goal either. But in 2013, the state of Iowa released the Iowa Nutrient Reduction Strategy, which was in response to the Hypoxia Task Force Action Plan that called for states that are members of the Hypoxia Task Force to develop comprehensive nitrogen and phosphorus reduction strategies, state-level strategies, to try to meet these goals. So we've been working on that ever since. This is just a map that kind of illustrates estimated nitrate-nitrogen loss in the first 6 months of the year from 97, so 10-year period. Mark David worked on from the University of Illinois. Kind of illustrates some of our problems. You'll see the central part of Iowa, Illinois, Indiana, Ohio, with very dark red, 15 to 25 kilograms per hectare estimated nitrate-nitrogen loss. So there are other maps that show similar type things, but one of the things that is somewhat unique about those areas that are in dark blue is those are also areas that the land areas benefit from artificial subsurface drainage, or commonly referred to as tile drainage. And so you see Iowa, southern Minnesota, Iowa, Illinois, Indiana, and Ohio. At a county level, some of those counties, greater than 60% of all the cropland or of all the harvested acres benefit from subsurface drainage. So that drainage takes that water that's leached from the plant root zone and delivers it directly to our surface water bodies. So that's a reason why we have a little different concern in some of these areas, because we're taking that nitrate that in Nebraska might be leached to shallow groundwater, and we're delivering it right to the stream with these drainage systems. Sometimes in Iowa, people say we only have nitrate loss from cropland where we have tile drainage. No, it's just that tile drainage serves as that delivery mechanism to the stream. As I'll talk about, it also provides us some other opportunities for removing that nitrate before it gets to our downstream water bodies that we might not have in other areas. Brian touched on this kind of as he starts to think about solutions, and thinking about our cropping system, I think, is very critical. Sometimes in Iowa, even from some folks I work with at Iowa State, they talk about the exponential increase in corn acres in the state of Iowa. That red line looks at the acres of corn, harvested corn from the 1920s to modern day. And what you'll see, we've consistently had 10 to 14 million acres of corn harvested every year. Even 100 years ago. But what's changed is that blue line, which is the acres of soybeans. So we've displaced small grains, oats, which are green, hay ground, alfalfa, a more perennial system, with soybeans. So now we are predominantly about 24 million acres of corn and soybean, about 14 million acres of corn, and 10 million acres of soybeans. If we think about ways to solve this in the future, thinking about a little bit more diversified cropping system could help us dramatically in reducing that nitrate loss, where compared to our annual system of corn and soybeans. So what can we do to reach these goals of a 45% reduction relative to the hypoxia task force? In 2010, we started a process of looking at literature that was available that documented water quality, performance of various nitrogen management and phosphorus management strategies, looking both at infield nitrogen management, some of our cropping system, and then these edge of field practices that I'll talk about. And we looked at data from Iowa, Illinois, Minnesota, Wisconsin, so similar cropping systems, similar soil conditions, relatively similar climatic conditions. And one of the biggest takeaways that we found is that there's no one single practice that's going to get us there unless we were to convert all of the acres back to a perennial system. We can make incremental gains with some of the 4R concepts, the right source, rate, time, and place of nitrogen fertilizer, but we're going to have to go beyond that as well. So if you look at those kind of darker mustardy colors, those are a lot of our 4R practices. And they're in the single digits to low double digits as far as nitrate reduction from those systems. It's not till we get to cover crops, which we found about a 30% reduction, or extended rotations, couple years of alfalfa, we see 40% reduction. And so this is what kind of illustrates we're going to need multiple practices if we want to get there. And just a couple pieces of data that illustrate that. Within a lot of north central Iowa, fairly high organic matter soils, we've done a number of studies looking at fall versus spring nitrogen fertilization, or in this case, we also looked at a split nitrogen fertilization. And on these soils, probably a little different than what Brian and you would see in Nebraska, we see little difference in nitrate loss, or the concentration of nitrate, when we apply fall anhydrous, when the soils are 50 degrees and cooling, and a spring nitrogen application. So certainly we would recommend applying that nitrogen as close to when the crop needs it as possible, but in many areas of Iowa, we're just not seeing a huge nitrate reduction if we move from that fall to spring. If we look at the green of a split application, so the upper left is the corn phase for 3 years where we have subsurface drainage monitoring, and the bottom right is the soybean phase. So we have both phases every year, and it's rotated corn and soybeans. What you'll see in all of these is that we do see lower, in some cases statistically significant, lower nitrate when we have that split application compared to the fall and the spring. So that green one is consistently lower than the red or blue bar in those cases. We also have a system with no nitrogen application. Tell the story that had a soil fertility expert from the East Coast tell me one time, Matt, if farmers in Iowa would just apply the right amount of nitrogen at the right time, there'd be no nitrate problem. And then he went on and said, actually, there'd be no nitrate in the tile drainage. And I thought, oh, I wish it was that easy. The blue bar, this is a system that we have 3 years of data on. It has not had any fertilizer on those systems since 2013. It's grown corn, soybeans since then. We're still seeing between 8 to 10 parts per million nitrate nitrogen in that drainage water. So even if we look at this, kind of illustrated in the next slide, if we were to meet our goals of a 45% reduction, we'd almost have to go to no nitrogen application in our corn soybean cropping system in the state of Iowa. An average rate might be 160, 170 pounds of N per acre. If we went from 160 to 170 down to 0, that ends up being about a 45% reduction in nitrate. This curve here is relating the nitrate concentration from a combined corn soybean cropping system to the nitrogen application rate to the corn in that system. Certainly rate matters, but as we start to get closer to those recommended rates of 160 and maybe a little bit below, that curve starts to flatten out. Okay, so some of the things that we can do, we want to do the best job with nitrogen management, but as I said, we're probably going to have to look at a few other things. So we've been looking at cover crops as well. We can see kind of a difference in growth depending on where we're at. Ames right in central Iowa. Gilmore City is about 60, 70 miles north central Iowa. So in Ames, we can grow cover crops a little bit better than they can in north central Iowa. We're working with growers to see how we can optimize that growth throughout the state. But even at a site where we don't get the best growth, when we monitor what's coming out in that tile line, that subsurface drainage system, in this case at that site at Gilmore City, we see about a 35% reduction in how much nitrate is lost. Now, one of the other questions I've gotten is, what happens under a perennial system? And sometimes I've had groups say, well, the nitrate loss is probably the same under a perennial system as it is under corn soybean because we have the same soils. So we have a study site where we looked at prairie. We went in and seeded the prairie in 2008, established new drainage plots, and this follows through from 2010 through the end of 2016, cumulative nitrogen loss from a continuous corn in red, continuous corn with cover crop in blue, and then the other two are prairie, either no fertilizer or 75 pounds of nitrogen per acre per year to that prairie. I think we see just a little bit less nitrate loss under our prairie than our corn soybean systems. We've done the statistics, those are statistically significant, the difference between corn and then the prairies. Okay? Now, is there economic use of that prairie? Not right now. But as we think about toward the future, perhaps there could be some use for perennial biomass. Okay, very quickly, some of the other things we can do, as I said, that drainage is a blessing and a curse. It's beneficial for our crop production. It exports nitrate, but we know where that nitrate is then coming out and how it's getting to the stream. So we have things like, we can use denitrification to help us. And so some of the practices, one is this subsurface drainage bioreactor, carbon-filled trench. Right now it's wood chips that we are routing that drainage water with nitrate in it, promoting denitrification, and seeing lower nitrate water coming out. We have systems where we're taking buffers that are out there where that tile line might be going right below the buffer. We're not seeing any nitrate reduction of that buffer, and we're trying to reintroduce shallow groundwater flow below that buffer for denitrification or plant uptake in that system. Another one at a larger scale is that we're strategically siting wetlands where we can intercept surface and subsurface flow to promote denitrification. So if we have one of these wetlands where we're able to route that water through there, so the wetland pool itself might be 1% of the contributing area, from about 100 site years of monitoring, we would estimate about a 50% reduction in nitrate from those landscapes. So if we take 1% of the land to remove 50% of the nitrate and maybe provide other benefits, it sounds and looks can be fairly attractive. Kind of the newest one we're looking at is drainage water recycling. So looking at the irrigation that you do in Nebraska, but taking that drainage water, storing it on site, and using it for supplemental irrigation. By doing this, we can reduce the downstream nutrient flow, but we really don't know whether economically this will work. So this is a practice that we're just starting to look at. And the last thing I will say in the last minute or last 30 seconds I have is the scale of change that we need in Iowa if we want to reach this 45% reduction goal. And this is just one estimated scenario that might get us there. We do the best job we can with end management on all of our acres. About 60% of our acres have a cover crop, so we'd need about 12 plus million acres with cover crop. We need about 27% of our ag land treated by a wetland, so about 7.5 million acres where the water from those 7.5 million acres goes into a wetland. And we need water from about 6 million acres going through a bioreactor. And as one of my bosses, John Lawrence, says, these are ands and not ors, okay? And to kind of say where we are right now, we might need 12 million acres of cover crops. We might have 1 million. Wetlands, we might need 7.5 million. We might have 150,000 acres treated by wetlands, and bioreactors maybe a couple thousand acres. So we are a long way from getting there, and the scale of change that we need is quite daunting. But I think there could be payoff as we try to pursue this, both improved local water quality. Some of these practices may protect and enhance the value of our soil resources. If we're going to put in and treat water, treat 7.5 million acres with wetlands or 6 million acres with bioreactors, there's going to be economic opportunities for engineers, other service providers to help farmers, help watershed projects get those practices in place, and ultimately we hopefully have a little more diverse landscape that can support some of the ecosystem services that we want. With that, turn it over to the next speaker.
Great, thank you for having me. I'm Martha Kauffman with World Wildlife Fund. Do I press this to start? Yes. Oh, I went back. How do I go back? Okay. Great. So I'm going to take us in a little bit different direction. We've been talking a lot about cropland and the challenges of maintaining fresh water. And I'm going to look at the flip side of this and look at the grasslands of this region and their role in conserving fresh water in the Mississippi River Basin. So if we look at the Mississippi River Basin, it's made up of these sub-watersheds, the Missouri River Basin being the largest one of those, also with the longest undammed river in the lower 48, with the Yellowstone River, the longest river in the United States, with the Missouri River itself. And if we look at the nitrogen pollution, which is a map that I think people have seen a lot, and you look at where that's coming from, it's from mostly the cropland areas, and these guys are doing great work to address that. If we look at the Missouri River Basin, that's outlined in blue on the left side of this graph. That is largely not in cropland and largely not contributing nitrogen pollution per the last speaker's slides. And the other region I want to just point out on this graph is the Northern Great Plains, which is the region that I'm focused on, the World Wildlife Fund is focused on, and that's the black dashed line on the top left. So what is holding all this together are the root systems of the prairie plants. There's in the Northern Great Plains alone, there's almost 1,500 different species of native plants that make up the diversity of life on the prairie, both above ground and also below ground, with this extensive and impressive root system below ground. And I like to point out with this slide that on the very far left, the little tiny roots, that's Kentucky bluegrass. And so what are the benefits of this prairie ecosystem and what they provide? Of course, there's carbon storage in the soil and the root system, that root system pulling the carbon down underneath. Wildlife habitat, the Great Plains have been called the Serengeti of North America. Once upon a time, they supported vast herds of bison, pronghorn, elk, grizzly bears. They are still critically important for most of those species. Cattle have replaced most of the bison, but we also still have large herds of pronghorn, swift fox, sage grouse, prairie chickens if we're here in Nebraska, and a number of migratory birds that come from far away to breed in the grasslands of the plains. It's also important for filtering and storing water, for drinking water, as we've just heard, and for producing food. The grasslands, while they may not be producing corn and soy, they are producing beef primarily in this region, and so they are turning, and we heard Galen Erickson earlier today talk about the value of cattle in converting non-edible ecosystem into something that people can consume. And in supporting livelihoods. This is a picture from Branding in Montana. The communities, I think that in the areas that are still in ranching, something like 72% of those are owner-operated, as opposed to when you move into the croplands, that gets down to below 50, around 40%. So communities that are still in ranchlands also are supporting a number of people. So the biggest threat to this ecosystem is conversion. And it's converting from native grasslands to croplands. Grasslands globally are the least protected, most converted biome on the planet, particularly temperate grasslands, of which the Great Plains of North America are the largest extent, and historically the largest extent of temperate grasslands on the planet. There's really only 4 places with extensive temperate grasslands left: the Great Plains of North America, the Kazakh steppe, Mongolia, and Argentina. So this is a unique and important area for a number of reasons. And it's going away pretty fast. It's slowed down in the last few years, but on average since 2009, the rate of loss is exceeding the loss of rainforest in the Brazilian Amazon. Because we were concerned about this, we started tracking it year to year through something we called the Plow Print report. And really our goal with that is to track the remaining intact grasslands. So what you see on this map, we're doing it at 2 scales. One, the larger scale is the Great Plains as defined by the CEC, and then the white area is the Northern Great Plains, which is the region that we're focused on. This is a report we started in 2015, and we're doing it annually. The remaining intact areas in the Great Plains is about 355 million acres, and in the Northern Great Plains, 127 million acres still in intact grasslands. So the brown is what's been plowed. The orange is what was plowed in the last year, so in 2017. That, you'll see, South Dakota was a real hot spot. In the Great Plains, we saw about this, in 2017, that first number is inaccurate. It was 1.7 million acres, which was a decrease from 2016, and about 53% of the Great Plains is still intact. And what's it being planted to? Primarily wheat, with an equal amount of corn and soy, and then canola after that. In the Northern Great Plains, we saw over 500,000 acres plowed up in 2017 alone. That's also came down from 2016, and almost 70% of the Northern Great Plains is still intact grasslands. And interestingly, it's a little bit more scaled towards, or slanted towards wheat in the Northern Great Plains, with 45% of what's being planted on newly converted areas being wheat, and smaller amounts of corn and soy, and then after that, lentils. So what's the correlation between soil quality and conversion? If we look at, this was an analysis of the Great Plains looking at that question, and the percentage of grasslands that are remaining on poor and marginal soils is 87% in the Great Plains and a little over 70% in the Northern Great Plains. So not really a big surprise. The best soils are our farmland, which is rightfully so. But even so, we're still seeing quite a bit of plow up on marginal, poor to marginal soils 17% or 63 million acres since 2009 in the Great Plains, and 15 million acres in just the northern Great Plains. So on poorer soils, I think that probably the pounds of nitrogen required per acre goes up. And so I think the potential for impacting freshwater is also significant. So when we talked about some of these impacts of the plow-up with the release of soil carbon, I've seen estimates of somewhere around 40% of stored carbon being released upon plow-up of native prairie. Habitat loss, that very sharp declining curve there is 4 species of migratory grassland birds that have declined somewhere between 70 and 90% since the 1960s, and that's mostly attributed to habitat loss. Increase in nutrients, which we've heard about. Of course, diversity of plants replaced by monoculture, or less diversity anyway, and then shrinking communities. So we did an analysis of quantifying what if the remaining soils of the Missouri River Basin. So now I'm going back to that because we needed to work at this at a watershed scale, and there's a large overlap between the Missouri River Basin and the Northern Great Plains. But what if we wanted to quantify the water quality and quantity benefits of avoiding conversion to cropland in the Missouri River Basin at landscape scale. So we worked with Limnotech and did a model looking at a large-scale screening level application of a SWAT model, and simulated water, sediment, nitrogen, and phosphorus from 1998 to 2013. And we ran 2 scenarios, a baseline scenario, what is the current mix of both cropland and grassland, and then a grassland conversion scenario looking at lands with soil quality, better soil quality, above 0.7 using Smith, and found that about 25 million acres are in the Missouri River Basin are still on good, better quality soils that could be converted. So this analysis was, what if all of that was converted? And using practices, typical practices that are used in the region. So we found that the surface runoff would increase by 26%, sediment would increase by 46%, phosphorus increase by 41%, and nitrogen by 31%. And this graphic shows you the watershed scale at which this analysis was done, and this is just the nitrogen graph. The benefits that were quantified are the protection of wildlife and aquatic habitat, protection of water availability, increased carbon storage, and reduced risk of flood frequency to downstream communities. There are a lot of drivers of conversion. That would take a whole nother talk, and there's been a lot of great research done on this. Certainly economics is a big one. The economics of farming versus ranching, it's more profitable, generally speaking, to farm than ranch. And the access to land, the cost of land, is a barrier to many people to enter ranching. Policy, the safety net for farming versus ranching, the safety net, the subsidies for crop insurance for commodity crops is relatively strong as compared to, for livestock producers, there's very little safety net. I think this year with the bomb cyclones and the polar vortexes and the flooding, there's a lot of people that are hurting without that safety net. And of course, there's a whole bunch of other factors of why someone would convert that relate to personal decisions and lifestyle choices. Solutions are also varied, and my goal here today is really to say, hey, if we want to protect the freshwater quality, let's not forget the importance of the existing grasslands and keeping them in place. So the way to do that, policy, farm bill, leveling the playing field for livestock producers, recognition of the benefits provided by livestock systems that are well managed on native grasslands in terms of payment for ecosystem services, technical assistance to help people transition and increase their resiliency and their profitability. Easements, of course, has been a long-term tool that's been used. It's not keeping pace with conversion, so we need more tools. And I throw out this idea of a conversion-free supply chain. In many parts of the world, there are approaches being used for deforestation-free supply chains, getting companies bought into the idea that they shouldn't be contributing to the loss of ecosystems, particularly in the Amazon. And there's some conversation about would a conversion-free supply chain be something that would be effective in this context. So my message is remember the Missouri, and remember the role of intact grasslands in conserving fresh water in the Mississippi River Basin. So thanks.
Okay. Back up a little bit. All right. Thank you, Dr. Ray and the Institute for the chance to share with you this morning or this afternoon. I want to start off with clarifying that I am not an expert on water issues in Rwanda. The 3 months that I've lived there do not qualify me yet as an expert, but I spent 30 years of my career here at the University of Nebraska evaluating and sharing information on water quality, so it's been very fascinating to evaluate the comparison of Nebraska to Rwanda, and so I'll do some comparison with you here this afternoon, and then talk a little bit at the end about what has drawn me there and what we're up to. So some statistics. It's very hard to compare Nebraska and Rwanda on a map. The size comparisons are very different scales. So some numbers to help you get a grasp of that. Rwanda is a country, it's not the smallest country in Africa, but it's very close. So it's landlocked and it's technically in East Africa, but it's kind of East Central Africa. The total land area is around 26,000 square kilometers compared to over 200,000 square kilometers for the state of Nebraska. So if you think in Nebraska, those of you who are from here, the three largest counties, Cherry, Custer, and Lincoln counties in Nebraska are larger than the land area of Rwanda. And in that land area are over 12 million people. So the population density there is almost 1,200 people per square mile compared to 25 people per square mile in Nebraska. So the population density and the intensity of agriculture in Rwanda is just different, put it that way. 70% of those 12 million people are engaged in agriculture in Rwanda, and the majority of people are growing crops to be able to survive for the next day. So they eat what they can find in their farm that's ready to harvest that day or the next day. Water resources in Nebraska, if you compare Nebraska from west to east, the rainfall ranges from a little over 300 millimeters a year to close to 900 maybe. Rwanda is on average well above that. The annual rainfall is 1,000 to 1,500 millimeters a year. And I'll show you a slide in a minute that shows the distribution of that rainfall. One thing that I have very much enjoyed was not being here this last winter in Nebraska. The average temperature in Kigali, where I live, is around 72 degrees Fahrenheit. It's equatorial or tropical in nature, but it's also relatively high elevation. So the elevation is 1,000 to 1,500 meters on average, although there are some mountains in the north that do reach significant elevation. So that combination of equatorial location and elevation makes the temperatures just extremely pleasant. There's a lot of water in Rwanda, and the numbers that I was able to find just were a little surprising to me. In terms of marshlands, lakes, and rivers, over 800 rivers in a country this size. I'm not sure exactly what constitutes a river yet in Rwanda, but still, there's a lot of water, and a lot of water moving across landscapes that are not typically seen in Nebraska. So this photograph on the right is north-central Rwanda. As one goes north in Rwanda, it becomes more mountainous, and people still farm. Some of the farming that I've seen on slopes is just pretty amazing. Occasionally, those are terraced. Some of these fields that you see in the background here are terraced, but many of the fields are not. And so their cropping system, erosion is basically something they live with. And that's probably the main issue in Rwanda that we'll come to in a minute. This is the annual rainfall distribution for the city of Nyamata, which is the largest city of any size to where I will be living eventually, soon, in Rwanda. It's in south-central Rwanda in the district of Bugesera. It's a bimodal distribution, so 2 rainy seasons. Right now, I left the peak of the rainy season to come here. April is their highest rainfall month, and then once one approaches June and July, the rain is done. And so those 2 rainy seasons, the largest one here in March, April, and May, the second one, a secondary rainy season in September, October, November, constitute their 2 primary growing seasons as well. Now with irrigation, one can add a 3rd growing season. So the temperature is there. If you have water and soils that are productive, you can grow 3 crops. But this rainy season that's occurring here, February, March, April, on into May, is also the peak of erosion that's occurring in Rwanda. And I'll have some slides that illustrate that here in a minute. So the 2 concerns that I see in Rwanda are unrelated to what we've heard about so far. Basically, nitrate is not an issue, and nor is phosphorus in their water. So this is the most recent data that I could find in the time that I have, and it's not that recent. It's about a decade or more old. But it documents water quality issues in major river drainage systems in Rwanda. And so the yellow line that goes across here are the World Health Organization targets or standards for water in river systems. And then these are these other major river systems in Rwanda. I'll concentrate on the Nyabarongo River, if that's somewhere close to the correct pronunciation. That's the river drainage system that covers the area that I will be living in. If you note the pH, nitrate, and phosphate levels, they don't measure nitrate in water in parts per million. Part per million would be nice in some cases. These are nutrient-starved production systems, particularly for nitrogen and phosphorus. So there's nothing really left to lose to groundwater or to surface water. What is left to lose is sediment. So the last column, if you look at these units for turbidity, FTU, the WHO standard for turbidity is 5 units, and the Nyabarongo River exceeds that by several hundred. Sediment is a primary concern. So sediment from erosion loss, it's not just taking the nutrients away, it's taking the capacity to sustain their productivity. So it's not just a health issue in the water quality that's impacted, but also health in terms of capacity to grow crops that are meeting the needs of food security in the country of Rwanda. And then, so I'll come back to the second issue of sewage and manure discharge a little bit later. I was really watching for opportunities over the last few months to get some good photographs to illustrate these 2 points. I didn't see the best photographs to show erosion, but this is what I have. So I live in, for now, the capital city of Kigali, in a very comfortable, fairly affluent part of the city. But just around the corner, down the street from me, are these small-scale, smallholder farms, right in the middle of a city of 1.6 million. And so the photograph on the left is showing this field, the block from my house, cropped right up to the edge of a ditch. So these constructed rock drains that run everywhere through the country are just abrupt ditches that carry water flow away. So they are growing these beans with what they have is a hoe right up to the edge of the drain, and so water runs off of that field with the sediment from that field and into the drain that's on the right, carrying sediment downstream, or at least to where it will settle out. That's a small illustration. What I have seen evidence of across the country is massive signs of erosion and sediment loss. It's not uncommon to see landslides where rain has caused soil to erode off a steep area and slide onto the road and block the road. So the loss of their livelihood through sediment loss is just a major issue in Rwanda. And then the second is lack of capacity to handle output from either livestock or human waste products. As part of the establishment of the institute that I've gone there to help get started, we've been looking at our livestock enterprises, and one was to visit livestock enterprises around the country. So we made this visit to a dairy outside of Kigali. It's relatively large. They milk 40 head of cows a day. And this is the door to their milking parlor, and we were there to learn how they deal with their milking parlor waste that they generate during washdown to clean where the cows have been. So what they said, they sweep the materials out this door onto this concrete apron, and then the manager here is pointing. He says, we get it on the apron, and then it goes that way, off in the distance, and that way was down this drain here, down this ditch here, and into this stream here. And if you look back up on the hill, that's where the dairy was. So that's basically how their waste are handled, to move it off the property into a stream. And then you go several miles down that stream, and people are pulling water out of that then to drink. Lastly, just some points about why I'm there. I've gone to help get started this institute, the Rwanda Institute for Conservation Agriculture. This is a joint effort of the government of Rwanda and the Howard G. Buffett Foundation. Our goal is to establish a land-grant modeled institution in Rwanda that teaches the approach of using a sound academic or teaching environment along with outreach or extension to growers and applied research to tie those efforts together. Our focus is very much on conservation agriculture and One Health principles. We are starting classes this September with 84 students, and will lead to a Bachelor of Science degree with specializations in 4 different areas. These are the principles that we're going to be teaching, researching, and extending, starting with soil quality and productivity as a basis for improving life in Rwanda and East Africa, to apply inputs appropriately at scales that are spatially appropriate, to efficiently integrate cropping and livestock systems to maximize productivity and profit at the same time, and to manage all of these systems in ways to minimize the impact on environmental quality. The Institute is going to have an experiential education focus, so students will live on farms and work on those farms. The second year of a student's career will be focused on cooperative and enterprise scale production systems. We will have curriculum threads that go throughout the 3 years of our degree on conservation agriculture, One Health, communications, and entrepreneurship. And then lastly, just some photographs of where things stand as of a couple of weeks ago. As I mentioned, our plan is to have students in class September 9th, and this is the extent of one of our first year dorms right now. The campus is under construction. The lake that we're based on is in the background here in the distance. This is our effort to try and control erosion in one of the drains that runs through campus. When I was there 3 weeks ago, they were trying to get ahead of the rains to prevent further erosion. The site is on a former location of a federal research facility that had existing orchards of mangoes and oranges. So this is on the edge of the lake where some of those orchards are located. And then finally, a photograph of some of the construction where we will have our vegetable and tree fruit enterprise building with some of our teaching and lab facilities. And I think with that, I will stop Chittaranjan and we'll see if we can go into the discussion. Thank you very much.
So thank you, Richard, and thanks all the four panelists. So we have two microphones on the center here. So we are ready to take questions, and I hope, yes. And please identify yourself if you can.
Wei Liao, Michigan State University. Very nice talks, all of them, all of you. Actually, I have a question particular for Matthew, for Iowa's case. And you talk a lot about, those treatment-based, the technologies to handle the nitrogen plus, phosphor. Of course, phosphor didn't mention on that on your case. And I like your statement ends. Those solutions need to be, together and to address those issues. But one big ends I didn't mention, I guess part of that, is about the soil biology. Soil is, the body to support all those kind of growth, those kind of stuff. Could you comment on that? Any, the perspective? USDA ARS jumping that, like, the Illinois, the prairie, the stations. They have a group of scientists working on soil biology and trying to improve the quality besides those plant rotation, those kind of stuff. And could you give a comments on that piece? And probably, Brian, you can comment on Nebraska's case as well. Thank you.
Yeah, that's a good question. And certainly, I guess a couple comments. I think that some of our different cropping systems of cover crops, extended rotations could really help us build our soils, improve our soil health. So there would be kind of additional benefits, but we also have something growing there a greater percentage of the year to take up nitrate. One of the things that we have found, though, we have a site where we've done no-till for about 20 years with in that case, actually, liquid swine manure. So it's a liquid swine manure system, no-till versus a conventional till. And what we've seen is that we see almost the same nitrate loss from that no-till system as the conventional till. So no-till has a lot of benefits from a soil erosion standpoint, maybe a phosphorus standpoint, soil health standpoint, but we still see nitrate loss from those systems. And so I think that just illustrates that, some of the practices that we have can be very effective for certain nutrients or certain pollutants, but may not be quite as beneficial for other factors in there as well. And certainly your point, the ARS unit there in Ames, the National Lab for Ag and the Environment, has done a lot of work on soil health, soil quality over the years, and collaborated a lot on various work. In fact, that long-term no-till site was started as one of the MESA sites long ago, well before I was at Iowa State.
Any similarity or difference with Nebraska, Brian?
Yes, hi, my name is Jenny Barron. I'm from the Swedish University of Agriculture Sciences. We struggle a lot with water quality and nutrient loads to our marine environments, including the fresh water resources. So I wondered, the scale that you seem to suggest for the Iowa case in particular, of the need to implement, how do you intend to do that? Do you subsidize farmers? Do you support them to do this implementation financially mainly? Or do you have some other mechanism or suggestions of mechanisms? Thank you.
Well, I wish I had the answer to that one, because that's the big question. I mean, I think we have the tools there to make measurable gains as far as, if we implement this, we can see improvements in water quality. The challenge is now is how do we accelerate the level of adoption? As some would say, we need the kind of the hockey stick. We're going along at this, and we need to be going along like this. So right now, a lot of it has been through cost share programs, incentive-based programs to get farmers to implement these practices. But I think people are really starting to think about how do we, that we're not going to be able to kind of cost share our way out of this. We're going to have to go well beyond that and looking at different mechanisms. That's where I do think, kind of thinking about this whole system, integrating livestock and cropping systems. We have cover crops. They in the short term may not be economically beneficial for the farmer, but if they have a grazing need, then those can be economically beneficial. I also think policy is going to be very important. I was excited to hear, or very interested in the policy of how do we provide some safety net for those livestock producers. Not as on as broad a scale as in the northern Great Plains, but certainly in some areas of Iowa, I've heard farmers tell me they've gotten out of grazing beef cattle because if they planted crops, they could reduce their risk. And so how can we have policies that can kind of get us having some of the perennialization on the landscape, I think is also very critical.
Anything to add, Martha, from your perspective in the Great Plains? The safety net issues.
The what use?
Safety net.
Oh, the safety net. Yeah, the safety net is a big driver, I think. We got a little bit of headway on that in the 2014 Farm Bill with a sod saver initiative that basically says that if native grasslands are plowed under, that a significant part of the subsidy for crop insurance is taken away for 4 years. And that was tightened up a little bit in 2018. So that was a little bit of headway on that particular issue, but it doesn't, it takes away some incentive to plow, but doesn't necessarily help the people when we have tough times like now.
So this is obviously national pick on Matt Mott. But Matt, I enjoyed your presentation, but so what's been the discussion about what happens to the nitrogen that goes into the denitrification part of this in terms of the impact on watersheds downwind and those kinds of things? I mean, it seems to me it's maybe fixing it one place and creating a problem somewhere else. So I'm just curious about your comments. And we have the same thing going on in Nebraska in places. So I mean,
yeah, that's a really good question, that we don't want to trade a nitrate problem for a nitrous oxide greenhouse gas problem. So actually there's been a fair bit of work looking at that. I'll say a little self-serving, some of it funded by the Iowa Nutrient Research Center, but looking at bioreactor saturated buffers in wetlands on nitrous oxide emissions. And what most of that work has found is that if we look at, say, the wetland, for example, the nitrous oxide emission off that wetland is about similar to that equivalent land area if it was under agricultural production. But it's treating, a lot more, 100 times more acres, actually. So actually, the nitrous oxide emissions off those are very minimal for the land area they occupy, and we're seeing similar with the saturated buffers and the bioreactors, so that, those systems, most of that nitrogen is converted to dinitrogen gas rather than nitrous oxide. That doesn't even take into account that, some of that nitrogen that might have gotten into the stream without those practices, the nitrate might be denitrified as it moves down the stream system, and there would be nitrous oxide emissions off of that. So I think these practices, certainly we need to continue to evaluate them, but from the research that's been done to date, it does not seem to be a huge issue, because we really seem to be getting complete denitrification in the systems.
Following up the policy perspective, on a national level, we've heard a lot of discussion recently about the change in regulations in terms of the Clean Water Act and extending during the Obama administration of those regulations to small tributaries and so forth. And then the Trump administration rescinding those regulations. And I just wonder what impact that discussion has on the ground programs that you all are focusing on.
I think very little. There's been a lot of question about what's considered water of the U.S. or not, but I think in actuality, it didn't necessarily impact the practices that we are looking at. There are some interesting issues with some of these practices as far as if we look at some of the mitigation or permitting process. I won't get into it, but with the wetlands, in some of these areas where we've put these wetlands, it's at the start of a drainage ditch, so it's a start of a man-made conveyance. But depending on what program they're put in under, if we put that wetland over top of that drainage ditch, we have to do, or they have to do stream mitigation for that section of man-made drainage ditch, which they're putting a wetland on. That actually could impact kind of the scalability of that program, and actually we're looking at different wetland models that would get out of those positions. So it's not really directly related to the water of the U.S. Necessarily, but kind of related to some of the federal policy of implementing some of these edge of field practices.
Hello, I'm Nancy Meyer. I'm with the Lower Platte North Natural Resource District, and my question's for Martha. You talked about using prairie, natural prairie, to protect the Mississippi River watershed, and I'm wondering what you would say would be the incentive to get the landowners to do that, given that their traditional approach is to obviously plant that and get a profit off of that. I know you talked about the benefits, but I'm not sure that they would see those as equivalent to the profit they get from growing crops. And I'm also thinking about why they would want to do it, considering that it helps people downstream, and it's not helping them so much. They'd have a lower incentive. So maybe there are some programs that you know about that would help them want to do that, or maybe there are some ways that we could get them interested in growing flower seeds, for example. Wildflower seeds are pretty lucrative, actually, to collect and sell. So if you could talk about that, please.
Sure, thanks. So what I've been primarily focused on is less about restoring and changing what people are currently doing. We've been mostly focused on keeping what's left in grass. So those are primarily been focused on working with people who are already doing livestock production, not necessarily asking people who are farming to go back. I think there's an argument for that on real low quality soils for restoration. And yeah, I've also heard native seed, for restoration in other places is very lucrative if you have the right conditions to grow it. So there could be a good financial incentive with that. In terms of incentives, and I was focused again more on what's currently in livestock production, so sandhills and north. That's where I think we have to get creative about actually helping people stay in business with some of those incentives that do recognize the role they're playing in maintaining clean water, clean air, wildlife habitat. Got a lot of those species of birds that are really dependent on that. If more birds or other things are listed, that's more burden on people, and nobody wants that. So I don't think we have mechanisms in place yet. But I'm putting it out there to encourage some creative thinking in this room. I know there's a lot of people working on ecosystem markets and other other approaches. I know of one approach that the Noble Research Institute is pursuing on ecosystem service markets. They're working directly. They've engaged some of the very large companies like General Mills, Monsanto, and other companies in developing a scheme for a private market that would pay producers for the ecosystem service benefits that they can measure. And so they have to develop a protocol and a verifiable system to sell credits and all of that. It's a big challenge, which is why we don't have those markets all over the place right now with respect to carbon. I think water is more advanced than some of the others, but in terms of water, carbon, and biodiversity, they're looking at all three of those. So that to me is a potentially exciting opportunity.
I'll just add, we've been doing work on buffer strips, but kind of specifically prairie, diverse prairie, so prairie strips that was in the most recent Farm Bill actually called out, so we're working on developing a technical note or practice standard around that, but it'd be taking small portions of the field and putting it into prairie to try to provide disproportionate benefits, and that would be something that would, there would be cost share programs for that. I'd also, while maybe the vegetation might be a little different, there's emerging work trying to look at return on investment for each part of the field. How can we use precision agriculture? And if we're consistently losing money on some parts of the field, which we are in certain areas of Iowa with depressional areas in particular, and yet every year in most cases, we continue to put inputs in there even though we're losing money. And so, I think there may be some areas where, we need to think about, getting the return on investment for each parcel of our field, and it may be that some of those areas, putting them into native vegetation, maybe provides us greater return for the overall field, irregardless of a program that's out there. I've had a farmer tell me before, I wish my yield map, instead of having a yield map in the combine, it was return on investment, or profit map in the combine. And maybe I'd start to think about each part of the field a little bit different if I saw it, red 9 years out of 10.
Thank you.
I'm Jerry Steer from York. I am familiar with all the problems we have with nitrates, and I'm not going to go there. I'm going to go to Richard Ferguson because he's been sitting there and has had nothing to say. So it's his turn. What I'm questioning is when you looked at the turbidity of the water, there was only one stream there that was actually under the 5 parts, or what, I'm not sure what exactly how they figured that, but could you explain how come that one was so far below everything else when the others were like magnitudes above it?
Thank you for the question, Jerry, by the way. If you don't know, Jerry and I have worked a long time. Probably 1993 or 4, Jerry helped put in one of the very first variable rate nitrogen studies in the state of Nebraska. So Jerry is a conservation advocate from a long time back. But I'm afraid I can't enlighten on that. That data set that I took from was published in 2002. So things could have changed significantly since then. And I don't know those river systems well enough to be able to say. I know there is tremendous seasonal variation in turbidity. And right now it's probably the worst it gets at the height of the heaviest rainy season. But my guess is that may be a system that drains more non-cropped area. There are some national parks in Rwanda that are largely untilled. And so I would guess maybe they have areas that drain from those national parks that reflect the lack of tillage that's going on in those areas. It may be related to how practices were in 2002 versus how they are now 17 years later, but I think probably that's the largest area of impact that can be made is to reduce tillage. And that's hard to say when the only way that they have to grow crops is with a hoe, and to open up a place to drop a seed. That's a challenge for us at the Institute, is to introduce ways to grow crops effectively without so much tillage that occurs with a hoe.
Thank you. Appreciate the answer. And I know if there's a difference to be made, you'll be able to make it. Thank you.
I actually have a question for you, Richard. And many of you don't know, Richard was my advisor, my PhD advisor, so it's kind of humbling to sit here on the same couch with you here. I'm really intrigued by the fact you said there's the bimodal rain distribution, and in some cases you said they can, with irrigation, they can get away with 3 crops. So from our perspective, you start a crop new, that's when the vulnerability is. That's when the roots aren't established, that's when the leach, in our case, the leaching, but this sounds like the erosion potential would also be the greatest. So what conservation techniques are they implementing, given where they are, and what do you foresee through the RICA Institute pursuing? How are you going to accomplish this challenge, so to speak? Does that make sense?
One thing that I learned that I did not know was really what conservation agriculture means, particularly in sub-Saharan Africa. There is a very strict definition. FAO has a definition of conservation agriculture that is to minimize tillage, rotate crops, and to maintain permanent cover. And that's it. It doesn't have livestock engagement. So for our institute, we've broadened that definition beyond just the soil-related parameters. But it starts there. To minimize tillage is going to be a challenge when all they have is a hoe. But to offset that, cover crops. So it's interesting to see the interest in cover crops in the Midwest and in sub-Saharan Africa. And they have, temperature is not a constraint. It's always 72 degrees. So you can grow something if you have water. So cover crops, as long as they're not removing nutrients and water that you want to conserve for your crop that you want to harvest, is a tremendous tool that will be used. But then returning that residue back to the land, right now the residue is primarily removed for feedstuffs for animal or fuel. So they will harvest stover and use that for fuel. So bare soil is the norm. And then also rotation. A farm field that's used for cropping just to survive generally is not planted to a single crop. You'll see a maize plant and a soybean plant and a cowpea plant and a yam. It's just all intermixed, and when they harvest a crop or a plant, then they plant something else in its place. So there's not rotation to break up disease cycles, and that's a concept that we'll try and teach, to move away from always cropping the land always in the same way, to going from one crop to another in sequence to maximize benefits of rotation. Those are the 3 main core principles, and then also introducing the nutrients from livestock that are pretty much lost downstream right now.
Thank you.
I'm Ben, and I'm a grad student here. My question goes to Richard. Can you tell us from your experience here in Nebraska and back in Rwanda, what are the main lessons that Rwanda can learn from Nebraska that can be implemented there? And again, from the challenges you've identified, do you think, is there anything the government's doing, or is there anything the university is coming up with to address the identified challenges? Thanks.
Yeah, thanks, Ben. That's an interesting perspective, and I have not interacted with lots of farmers yet in Rwanda, but what little I have, what my observation is that at some level they're not different from farmers in Nebraska or Iowa or Montana. I think a problem that we have had in Nebraska, and probably also in parts of Africa, is major projects that come in with subsidies or cost share efforts to, there's value to those to introduce ideas that are new, but that's not the way to sustain practices by cost share. I think if farmers in Nebraska see that something is going to increase profit for them, that's a practice they'll adopt. And if it also is a practice that's going to, at the same time, decrease the environmental impact of what they're doing, that's a side effect that farmers recognize they're drinking the same water as people that live in Lincoln or in Kigali. So I think finding ways to encourage farmers to adopt practices we can show increase their profit are going to be critical for us to do, and not say, well, we'll subsidize this practice for you to try it out and expect that you'll always have that subsidy. We are working on trying to set up ways that we can be effective in extension in Rwanda, working with extension services that already exist and building that capacity into our institute. I can't really say yet how that's going to be done, other than conveying that knowledge in ways that's meaningful and understandable to farmers is really no different in Rwanda versus Nebraska or Iowa.
I see Molly standing up there, but I see also Professor Dahab has one question. So can we take one more question?
I guess this is Mohammed Dahab, Civil Engineering, UNL. I'll pick on math again. You referred to bioreactor, use of bioreactors, and I'm just curious, what do you mean? Is this an in situ process to promote denitrification, or are we talking about a mechanical systems to augment agriculture, or what?
Yeah, so what we're doing, or what's being done, is that they're digging a trench, they're putting wood chips in there, and then routing a portion of the tile drainage through that system, and promoting denitrification in there using the carbon in the wood chips, microbes, to convert the nitrate to dinitrogen gas. There are some folks looking at other carbon media for that. Colleague has a pilot scale reactor with corn cobs in it right now, because in Iowa, that scenario that I showed, we might need 120,000 of these bioreactors, 20-foot wide, 100-foot long, 3-foot deep, full of wood chips. We don't have that many wood chips in Iowa, and so some people are looking at other carbon sources, of corn cobs being one of them. So they're in situ, but kind of at the edge of the field, where we're just routing a portion of that drainage water through those.
Give a round of applause to our 4 panelists. And Molly had